Okay. All right, and then actually the book makes a comment that it probably should never even got into. Here we said that the set of strings that M accepts is called the language that M accepts. Not too controversial. But then the book says, well, we don't want to use that language we don't use those words for a particular reason. And so instead we're going to talk about recognizes. I think, if they just had said that in the beginning, then they wouldn't have to go back and make that change. So a finite state machine accepts or rejects a particular string. They want to use those words, accept and reject, when you're talking about a string. But when you're talking about a language, then the book wants to make the distinction and say that the finite state machine recognizes a particular language. Okay. All right. Okay. Then we can say a little bit more about what a computation is. Now that we've seen some finite state machines and we've seen how to describe them, what is a formal way to define a particular finite state machine, how do we talk about what a computation is? What is a computation on a finite state machine, a deterministic finite state machine? And by the way, I should have pointed out one thing. Why is this kind of a machine called a finite state machine? Well, we've got states, okay. Why is a machine? I don't know. But finite is obvious because the number of states here is finite, and I probably should have put that explicitly. A finite set of states. Okay. Which probably never would have occurred to you that there might be an infinite. There might be machines that have an infinite number of states. Well, you can certainly conceive of them, but we're talking about machines that have a finite number of states. So you can always write down a description of a particular machine that we're thinking about in this class. It will have a finite set of states. It's something that's writable. Okay, so what do we mean when we talk about a computation of a finite state machine that recognizes a particular language? Okay, so computation is there's a sequence of states called R0, R1 through Rn. This is a variable. There's some number of states that the machine goes through. And why are these called R and not Q? Well, okay, that's sort of a silly question. I just need to point out that we're using these Qs to talk about the specific states that are in the finite state machine. And here we're talking about a sequence of states that a particular computation goes through. So these variables R0, R1, their values will be particular states, they'll be particular Qs. But we're talking abstractly, then I need to use a different symbol. If I told you there's a sequence of states Q0, Q2, Q16, and so on, that's a specific list of states and not an abstract object that refers to the fact that there is some sequence of states. Okay, it's a very, very fine pedagogical point about the use of mathematical notation. Okay, so there's a sequence of states such that R0 is equal to the start state of the finite state machine we're talking about. Okay, so we're talking about the finite state machine M. So the sequence of states that the machine goes through, or the computation goes through, has to start with the start state of that machine. What else can you tell me about these symbols here? Anything else that's... Yeah. Okay, in sequence in what sense? N is bigger than what? No, I wouldn't want to put that way. These N's are subscripts for this series, in this sequence. Okay, this is a sequence of states, and this is the zeroth state that we were in, and everything Q0. It's the first state that we're in this computation, and the next state we're in this computation, and so on. Yeah.
Rn minus 1 has to share edge with 1.
Is that saying that?
Rn minus 1.
Rn minus 1. Yeah. Okay. I'll write that down, but I'll write it a little more formally. Needs to share an edge in M with Rn. But when you say share, what do you mean? Can you be more specific? Well, the edges have a direction. There's a who's on which end? Yeah, so the picture here share means Rn minus 1 to Rn. And that's true for n minus 1 and n. What about the other ones? Yeah, right. So more generally, Ri minus 1 goes to Ri when I is in the appropriate range here. Okay, so let's write that down. Again, we're trying to define in a more formal sense what it means for a computation. So delta Ri, and then you see the I plus first character in the string that's being computed on equals Ri plus 1. Function for this finite state machine has to have the property that when you're in state Ri of that sequence, and you see character, the I plus first character in W, then this delta function should be mapping this state and this character to Ri plus 1. That's the relationship between Ri plus 1, and this character Wi plus 1. And the fact that this is an I and I plus 1, that just has to do with the subscripting here. We started with a 0 for the states, but we start with a 1 when we're talking about characters in a string. Okay, terribly confusing. Sometimes the first element in something is element 0, and sometimes it's element 1. But you should all be familiar with that kind of confusion because you've been programming in C, right? Or C++, where in an array, the first element is what subscript? 0. Okay, that's a piece of insanity that got inserted into C and other programming languages causes no end of trouble. Sane people know that the first element in anything is element 1, not 0. But anyway, so here we're starting with 0 for one object, which is the sequence, but we're starting with 1 for the object which is a string. Okay, go figure. Anyway, you can deal with it. So this is what it means with the computation, that M is, there's a computation of, or on W, input W, is that there's some sequence of states which has this property. Okay? And then what do we mean that the computation accepts W? What does that mean in terms of this abstraction here? Yeah, Rn is in the final states. Okay? And rejects means that Rn is not in the final states. Machine M that accepts a language A that is all strings with an odd number of ones. Okay? So take a minute. Yeah, okay, so I had in mind, because I cheated and got it from the book, I had in mind a different solution, but the question first of all is, does this work? Okay, and why not? 0, 1, 0, so you get 0, 1, 0, you end up in Q1 and you reject. Okay, so it looks like this one is not quite right. More formal. Okay, all right, so I think the homework questions have you doing some design, and it's a puzzle. It's just a puzzle, really. Let's take a little time to do. All right, so now that we have a fairly clear idea of what a finite state machine is, both formally and informally, and we have done a little bit of design, there are things that we can prove about finite state machines. And in particular, there are things called regular operations. regular operations. So one is called union. So, actually, here's one more term. Sorry. One more term here. Definition. A language, L, that is recognized by some deterministic finite state machine is called a regular language. Okay. All right. And then we're doing these regular operations, which is union over regular languages. Okay, so this is a theorem. Well, actually, maybe I should define union first. So A and B are regular languages. Okay. Well, each language is a set of strings, so these are sets. Okay, A is a set of strings and B is a set of strings. It happens to be that A is a set of strings that's recognized by some deterministic finite state machine, and B is a set of strings that's recognized by some deterministic finite state machine. Okay, but they're still the sets. So what kind of things can you do with sets? You can take unions, you can make intersections, you can make differences. What's the exclusive or difference? I mean, you can do all kinds of things with sets. You learn that in high school. So you can think about the set A union B. Okay, that's the set of strings that are either in A or in B, or maybe they're in both. Okay, so we can ask, is A union B a regular language? And the theorem is yes. So if A and B are regular, then A union B is regular. Okay? That's a theorem. That's something we can prove. Now, is that really clear what it's stating? Again, think about A as a set of strings, and B as a set of strings. It happens to be a set of strings that's recognized by some finite state machine, and B is a set of strings recognized by a finite state machine. But because they're sets, they can be union, and so we can think about A union B, and this theorem says that if A and B are regular languages, then A union B is also a regular language. Okay? How do you prove that? Well, the only way we know so far to know whether a language is regular. Yeah, if it's recognized by some deterministic finite state machine, that's the only way we know so far. We're building up some tools, but so far, the only possible way of exhibiting or proving that a particular language is regular is by showing a deterministic finite state machine that actually recognizes that language. Okay, so we want a deterministic finite state machine that recognizes A union B. And under the assumption A is a regular language and B is a regular language, we know what about them? Accepted by what? Accepted by what? Okay, some. Okay, so A and B? No. Okay, so the question here is, what was being suggested here was ultimately getting to the point that what we know about A is that there is, because it's regular, there's some deterministic finite state machine that recognizes it. And what we know about B is that there's some deterministic finite state machine that recognizes B. Okay, again, by the fact that really the only way we know that a particular language is regular is the fact that is this fact, this definition. And so under the assumption A is regular or B is regular, we know that there's a deterministic finite state machine that recognizes A, and there's another one, which doesn't have to be the same one, it can be different, that recognizes B. Okay, so we've got these two deterministic finite state machines that recognize two different languages, and now we somehow want to use them to build, or to talk about how we would build if we actually literally had the finite state machine for A and the finite state machine for B. If we had those in our hands, how would we use those to build a deterministic finite state machine that recognized A union B? Any ideas? Well, union is kind of like an OR, right? You're saying, well, I'll accept a particular string if it's accepted by A or it's accepted by B. I mean, if it's in A or if it's in B. Okay, so you might think you do the following thing. Here's the finite state machine M1 that recognizes A, and here's M2 that recognizes B. So we have these two deterministic finite state machines, and we want to accept if and only if a particular